Hello friends, good afternoon. Welcome to yet another session, A Venture to Unknown, a talk on Latin squares and Greco Latin squares. So the story started in 1725, or some say it is 1694, when a French mathematician, Mr. Jacques Ozanam, arranged the 16 honors cards of a deck: Ace, King, Queen, Jack, clubs, diamond, hearts, spade. 16 honors card of a playing deck in a 4 by 4 array such that in any row or in any column there is no duplicate in denomination as well as there is no duplicate in suits. So we have ace, king, queen, jack, we have spade, diamonds, clubs, hearts. Or in the third column we have queen, ace, king, jack, clubs, diamonds, hearts, spade. So there is no duplicate in any row or in any column. In diagonals also the same property holds, but we don't consider it. We don't need it for our Latin square and Greco Latin square talk. So we can do it. There are two methods. I call it one I call replacement method and one I call placement method. So we start with the simple sequence: clubs, diamonds, hearts, spade, ace, king, queen, jack. We have to arrange them by swapping cards. We have to make such an arrangement that in any row or in any column there would not be any duplicate either in denomination or in suit. So we have king of clubs, we have ace of clubs, so I swap king of dice and king of clubs. It's taking time. Okay. Then I bring queen of hearts here. Queen of hearts here. Then I bring jack of spade here. So the first row is there is no duplicate in color and also no duplicate in denomination. Ace, king, queen, jack, clubs, diamond, heart, spade. Now I arrange the first column. So I cannot bring king of dice, so I bring queen of diamond. Then I bring jack of hearts. Then I bring king of spade. Okay, so first row and first column are all right now. There is no duplicate in suit and also in denomination. Now what left is this 9 cards 3 by 3 in the 3 by 3 array. So let's try it. We have king of diamond, king of spade. What are left are king of clubs and king of hearts. So king of hearts cannot be in the fourth row because king is here. King of heart cannot be in the third row because heart is here. So king of heart has to be in the second row. Now king of heart cannot be in the second position because king is here. King of heart cannot be in the third position because heart is here. So king of heart has to be in 2-4 position. So I'll bring king of heart here. So king of dice, king of heart, king of spade, king of clubs has to be here. That is fine. Then queen of heart, queen of dice. What are left are queen of clubs and queen of spade. Queen of spade cannot be here in the fourth row because spade is here. Queen of spade cannot be in the second row because queen is here. So queen of spade has to be in the third row. Now queen of spade cannot be in the third position because queen is here. Queen of spade cannot be in the fourth position because spade is here. So queen of spade has to be in the second position. So I'll bring queen of spade here. So queen of heart, queen of diamond, queen of spades, so queen of clubs has to be here. Otherwise there will be duplicate in rows and columns. Now jack of spade, jack of hearts. What are left are jack of diamond and jack of clubs. So jack of diamond, by the same argument, jack of diamond has to be in the fourth row and jack of diamond is in the right place. It cannot be in the second place. Diamond is here, cannot be in the fourth place because jack is here. So jack of diamond is in the third place. So jack of spade, jack of hearts, jack of diamond and jack of clubs is here, which is all right. Now I need to bring ace of spade here. Then I need to bring ace of diamond here. That completes the arrangement. There is no duplicate in either in suit or in denomination in any row or in any column. Now this I call replacement method. By swapping cards, by replacing cards, we don't need the cells to put the cards. Now there is another method which I call placement method, where you have cells. And if you follow the sequence, ace of clubs to jack of spade, so everywhere you put the first choice and you will get the arrangement. So I put ace of clubs here, then clubs is not possible here. Among diamond, ace of diamond is not possible here. So king of diamond is the first choice. Then queen of hearts is the first choice here. Then jack of spade is the first choice here. Now clubs cannot be here. Ace of diamond cannot be here. King of diamond has gone there. So queen of diamond is the first choice here. So so that's the way. If you go on following the natural order of reading and writing, and you put the first choice from the sequence, you get the arrangement. Euler coined the term Greco-Latin square because he uses Greek letters for the denominations and the Latin letters for the colors. So he used to call them Greco-Latin square, and we call it a 4 by 4 Greco-Latin square. Now there is another method. You follow the sequence of the card. So you start with ace of clubs. Now next is king of clubs. King of clubs cannot be here, cannot be here. So king of clubs comes here. Then queen of clubs comes here. Then jack of clubs comes here. Then ace of diamond. Ace of diamond cannot be in the first row, cannot be here. So ace of first position for ace of diamond is here. Now king of diamond cannot be here. King is here, cannot be. So king of diamond can be here. Then queen of diamond cannot be here because queen is here. So queen of diamond has to be here. Then jack of diamond has to be here. Then ace of hearts. Ace of hearts, the first position available for ace of hearts is here. Then king of hearts cannot be in the first row, cannot be in the second row, cannot be in the third row. Heart is here. So king of hearts only position is here. Then queen of hearts. Queen of hearts can be here. And jack of hearts has to be here. Now you have got unique choices, so you can complete that. This is another method. Now I know a trick. I know a trick where you can start in any random cell with a random card, and you can complete the 4 by 4 array, creating a new sequence. Then there will be again two methods. One using the first choice in the natural order, and second using the first choice of the cells and the new sequence. So that's a fun. Now some counting problems. How many 4 by 4 Greco-Latin squares are there? So for the 1 cell, I have 16 choices. I can put any card here. So the number of choices is 16. So once I put the card, number of choices in the 1-2 cell is 9. Number of choices in the 1-3 cell is 9. And once the first 3 cells of the first row is complete, the fourth cell is unique choice and has the number of choice 1. Then this 2-1 cell has number of choice 6. 3-1 cells has number of choice 3, and the 4-1 cell becomes unique, and the rest become unique. So the number of Greco-Latin square of order 4 is 16 times 9 times 4 times 6 times 3, which is 10,068. But comparing to the total number of possibilities, which is 16 factorial, which is of the order 10 to the power 13. So it is like trying 2 billion times randomly and getting the arrangement only once. So that hard the problem is. Okay, now the mathematicians are notorious. They don't stop at 4. They started trying different arrangements, and they found that order 2 regulating square is impossible. It is easy to demonstrate that order 2 regulating square is impossible. Similarly, when they tried 6 in late 1700, the 36 officers problem came up, which is nothing but the problem of building a regulating square of order 6. Euler got this problem, tried a lot, and made a systematic study of the regulating squares, but he couldn't construct order 6 regulating square. Finally, in 1901, the French mathematician Gaston Perry enumerated all 9,000 order 6 Latin squares and showed that the order 6 regulating squares do not exist. Okay, now probably when Euler was studying these structures, these regulating squares, he could create regulating squares of any order except 2, 6, 10, 14, 18, and he conjectured that regulating square exists except when the order n is of the form 4k plus 2. So for k equal to 0 we have 2, for k equal to 1 we have 6, for k equal to 2 we have 10, for k equal to 3 we have 14, and this conjecture was there for around 200 years. And finally, in 1959, Professor Rajendra Bose of Indian Statistical Institute and his student Professor Srikhande first constructed a regulating square of order 22, which is of the form 4k plus 2, 4 into 5 plus 2, thus disproving Euler's conjecture. Then Professor E.T. Parker of University of Illinois used his UNIVAC computer to develop an order 10 Greco-Latin square in uh, uh, order 10 Greco-Latin square, and Professor Bose, Professor Second, and Professor Parker together proved that Greco-Latin squares or mutually orthogonal Latin squares of all orders exist except 2 and 6. And it was a path-breaking paper. It was a front page news in New York Times. You can see Professor Bose, Professor Second, and Professor Parker, and the team was named Euler Spoilers. So here is an example of an order 10 Jordan square or order 10 mutually orthogonal square. This is just arrangement of 10 numbers 0, 1, 2 up to 9. Although we are calling number, we are not using any ordinal property. They are just 10 different objects. We are not using 1 less than 5 or 9 greater than 3, anything. So these 10 digits are just 10 numbers. The first digit corresponds to Greek letters and the second digit corresponds to Latin letters, or first digit corresponds to the denominator and the second digit corresponds to the suit, and this is a 10 by 10 Greco-Latin square or mutually orthogonal Latin square. Now since the digits are just used as objects, sometimes people demonstrate them using colors. Some studies, so 012120201 is a 3 by 3 Latin square in standard format. This is called standard format because first row is in the form 012 and first column is in the form 012. So this is a 3 by 3 Latin square. So this is the 3 by 3 Latin square we saw in the previous slide, 012120201, and there is another Latin square 3 by 3 which is different from the first Latin square 012201120. Just interchanging the second row and third row, we develop another 3 by 3 Latin square, and they are orthogonal. They are mutually orthogonal because if you superimpose the first on the second Latin square, you get all the 9 pairs. So you get 001122 122001 210210. So that's why these two order 3 Latin squares are called mutually orthogonal. Now this is for order 3. For order 4, you get a triplet of of order 4 Latin squares. The first one is in standard format, and first and second are mutually orthogonal. First and third are mutually orthogonal. Second and third are mutually orthogonal. For order n, there can be at most n minus 1 mutually orthogonal Latin squares of order n. And this is called a complete set. The proof is easy because the choice in the 2-1 position in the standard format is n minus 1. So there can be at most n minus 1 mutually orthogonal Latin square of order n. This is a simple brain teaser for order 3. I'm showing with colors. I'm not using digits. So the orthogonal 3 by 3, mutually orthogonal 3 by 3 Latin square, and there can be at most 2 of them. Then if you go to 4, you just follow the natural order and use the first choice, and you get the mutually orthogonal Latin squares. When you complete the first two, the third one becomes unique choice. You can click in any order. And that's a complete set of mutually orthogonal Latin squares of order 4. It's a nice brain teaser. Now one can go to 5. For 5, you have to put the symmetry button. For order 5, the Latin square has its orthogonal mate if and only if it is symmetric. Oops, I'm not getting it. Finally, I got the symmetric order 5 Latin square. Now, if you just follow the sequence, and take up any row, so you have yellow, red, ash, blue. Let me try it. Now yellow is not coming. Now yellow is not coming. Yellow, red, ash, blue. Then I copied from this here, from the first Latin square, ash, blue, red, green. So ash, blue, yellow, green, ash, blue, yellow. And that completes a pair. Now I try the hard one. Green, ash, yellow, red. Blue, yellow, green, ash. Ash, blue, red, green. That completes the third one, and the fourth one becomes unique. So that makes a complete set of order 5 mutually orthogonal Latin squares. These are nice brain teasers, but for 5 you have to start with a symmetric Latin square. That's a nice brain teaser. Now some applications. Suppose you have 3 types of fertilizers and 3 types of soils and 3 types of paddy seeds. Now to find which combination is the best, you need to have 27 plots to yield, to see the effect of fertilizer, soil, and paddy seed. But using Latin square design, you can do it in a 9 by 9 cell, a 3 by 3 cell. So you have first column you put fertilizer 1, second column you put fertilizer 2, third column you put fertilizer 3, first row you put soil 1, first second row you put soil 2, third row you put soil 3. Now you have all the 9 combinations of fertilizers and soils are present. Now use a Latin square design with paddy 1, paddy 2, and paddy 3, and you can find any combination of soil, fertilizer, and paddy seed. All the 27 combinations are present, and now you can measure the yield and do your experiment. So this is a tool in design of experiment, and it is called Latin square design. Now the application of Latin squares would be, suppose in scheduling. Suppose you are scheduling a tournament between two teams. Uh, one team has A, B, C, D, and one team has 1, 2, 3, 4. It's a ping pong tournament. Now every player of team 1 will play with every player of team 2, and it has to be done in 4 days, and each day has 4 time slots. So if you use the Greco Latin squares of order 4, you can make sure that all the members of team A are playing with all the members of team B, and no one is playing twice in the same day or twice in the same time slot. That's the application of regulated squares in scheduling. Now let me talk about some construction method. So to construct regulated square of order n, if n is prime or prime power, you can use Galois field of n with that addition, but n minus 1 addition tables will give you n minus 1 mutually orthogonal lattice squares. And then if n is, then there is another method which is known as canonical product construction. If A1, A2 are two mutually orthogonal lattice square of order A, and B1, B2 are two mutually orthogonal lattice squares of order B, then canonical product of A1 and B1 and canonical product of A2, B2 are two mutually orthogonal lattice squares of order AB. The construction is easy and the proof is also easy, but this is another method. So now given any number n, you can take its prime factorizations. For prime powers, you can develop the mutually orthogonal lattice squares, and using the Kronecker method, you can plug them to get a pair of mutually orthogonal lattice square of order n. But the problem crops up when n is of the form 2 times an odd number, 2 times 2k plus 1. Because for 2k plus 1, you can take the prime factorization and use and develop a pair of moles using Galois field and Kronecker method. But for this 2, you don't have any pair of mutually orthogonal lattice square of order 2 that I told. For order 2 and 6, it is impossible to have mutually orthogonal lattice square. So when it is 2 into 2k plus 1, or when it is of the form 4k plus 2, this method fails. We need special technique, and that's why Euler made his conjecture that for 4k plus 2, Greco Latin square and mutually orthogonal lattice square do not exist. However, okay, for when n is odd, if you take the ijth entry of one Latin square as I minus 1 plus j minus 1 mod n, and ijth entry of another Latin square as I minus 1 minus j plus 1 mod n, then a and b are Latin squares and they are mutually orthogonal. So that works for any odd order n. The proof is easy, and when I was playing with my sister Munjima in 1995, we developed this method, but this is a well-known result, and this works for any odd order. For even order, our method can be extended to cover 50% of the cells, whereas there is another method which is known as sequential method that I'll demonstrate. that works fine for odd order and for even order. It fills all the cells except the last n of them, except the last n of computers are very much used in this area. Professor E.T. Parker developed his mutually orthogonal lattice squares of order 10 using UNIVAC computers. So this is an example of computer-aided proof in early ages. And then it has been proved by exhaustive search that a complete set of 9 mutually orthogonal lattice square of order 10 does not exist. That has been proved by extensive computer search. But what about a triplet? Does a triplet of order 10 mutually orthogonal lattice square exist? That's an open problem. We don't know whether it exists or not till today. But what we could do is this example where these three Latin squares of order 10, first and second are mutually orthogonal, first and third are mutually orthogonal, second and third fail to be mutually orthogonal because there are some duplicates. See, you have 6, 1 here, you have 6, 1 here, so there are 9 duplicates. This is the closest we could go, but it's really a hard problem to try, and it's an open problem till today. Sometimes I think of triplet by birth. These sisters are working in UK as doctors and they are triplets. Small order lattice squares, Greco Latin squares. 3 by 3 Greco Latin square is like this in standard format. There is only one of them. For 4 by 4, there are 4 Latin squares possible in the standard format, and only one of them has a complete set. There are 56 order 5 lattice squares in standard format, and only 6 of them has complete sets or orthogonal mate. And for 5 by 5, it is an it if the lattice square is symmetric, it has its orthogonal mate, and also the converse. If it has an orthogonal mate, it has to be symmetric in the standard format. So I told that order 6 regularity square is impossible. However, I was fascinated by these columns 1, 2, 2, 1 for order 3, then 1, 2, 2, 3, 3, 1 for order 4, then 1, 2, 2, 3, 3, 4, 4, 1 for order 5. All of them have regularity squares, and for 6 it does not exist, and for 7 I'm still searching them. I took the column as it starts with 0, 0. First row is 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. And the first column is, I call it rotating column 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 5. Till today, I do not know whether such a Greco square exists or not. I tried a lot. I have some algorithms too, which tries to solve them, but I fail because there is a reason. Because the numbers of the Latin squares of order n in standard format increases explosively. For n equal to for order 1 there is 1 Latin square, for order 2 there is 1 Latin square in standard format, for order 3 there is 1 Latin square, for order 4 there are 4 Latin squares, for order 5 there are 56 Latin squares, for order 6 there are 9,408 Latin squares, which the mathematician Gaston Terry exhaustively enumerated for their orthogonal mate that came up with his proof that the orthogonal mate for order 6 standard format lattice square do not exist. But for 7, it goes to 16 million. So the jump from 56 to 16 million is huge, and I am failing to construct regular lattice squares of order 7 with the given column. I did an extensive study of order 5 regularity squares. There are 9 columns possible, and all of them have all the regularity squares of order 5 with these 9 columns exist. Now from Latin squares we can go to Latin cube. So for 3 by 3 we can partition it in 9 ways. So we have front, middle, rear, left, middle, right, top, middle, bottom. So we can try to fill them up. So that way it's easy to see that Latin cube exists for all orders. Now we can go to the Greco-Latin cube, and with a little bit of trial and error, we will be able to develop a Greco-Latin cube of order 3. For Greco-Latin cube, you need strings of 3 digits. One is in x-axis, one is y-axis, and one is z-axis. So 3 by 3 Greco-Latin cube of order 3 is complete. For 4 by 4, you just need to follow the natural order. Uh, that completes Greco-Latin cube of order 4. These are just 4 partitions, and I have occupied them with strings of triplets. And it's a Greco-Latin cube of order 4. For any odd order, I have got an algorithm that works. I mean, it is not random. There is a certain algorithm, and it can be used for any odd order Greco-Latin cube. Probably this will work for any odd order Greco-Latin hypercubes too, for higher dimensions. So that completes order 5 Greco-Latin cube. There are 5 partitions. For order 6, I tried and failed. And a probable extension to the 1959 paper would be Greco-Latin cubes and hypercubes exist for all order except 2 and 6. That's the probable extension. Now, I played with the concept of group Latin squares in 2020. Okay, so here we need to introduce, I mean, each row of a Latin square is a permutation of n objects. Okay, and 2 rows can be composed using permutation composition. So if you start with an acyclic permutation A, then 1, A square, A cube, A4 up to A n minus 1 form a subgroup, and this will constitute the rows of a Latin square. So that's a random method for creating Latin squares. Not only acyclic, not only acyclic computation, if n is composite R into S, then you can consider R cycles of length S or S cycles of length R, and can develop a group Latin square successfully. Now, what about its orthogonal mate? So for orthogonal mate, we need a concept called transversal. I'll demonstrate it. A transversal of a Latin square is a set of entries which includes exactly one entry from each row and column and one for each symbol. And there is a theorem that orthogonal mate exists if and only if the Latin square has n distinct transversal. And for group Latin square, I found that a transversal exists when n is odd. A transversal does not exist if n is 4k plus 2. A transversal may or may not exist. You have to search for it when n is of the form 4k. And that the transversal does not exist for 4k plus 2 uh, says that it is impossible to have a orthogonal mate of a group Latin square of order 10. So this is not the way to find a group Latin square of order 10. I am writing down the paper, but it will take time. So for order 5, suppose I start with an acyclic permutation. 3 goes to 1, 1 goes to 2, 2 goes to 0, 0 goes to 4, 4 goes to 3. And this is the group Latin square where all the rows are forming a group under a permutation composition, and then you can search for the transversal. For odd order it exists. If I try for other orders, if I try for 4, let me see, I can use 2. I can use two cycles of length 2, and then now it's orthogonal may or may not exist, but it is existing here. But it may not exist. If I use acyclic permutation, then it says transversal of 0 is not found, fails to find the transversal. Now there is a concept of blocking. So for a 3 by 3 regulated square, where if I put 0, 0 and 1, 1 in different relative positions, this 6 combination, you won't be complete the regulated squares, and for these 6 combinations, for arrangements, you will be able to complete the regulated square. So given an n by n array, if I put 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6 points, 0 is the only position for 0 is here. So if I put 0, 0 in 1, 2 position, you won't be able to create a regulated square of order n with these entries. So that's a blocking. Now I can go down from n to n minus 1. In the diagonals, if you put a transversal 0, 0, 1, 0, 2, 0 and then 3, 1 here, then 3, 0 has the only position here, but there is no place available for 4, 0. It can't be here, it can't be here. So there could be a theorem that given an n by n array, one can put n minus 1 entry so that it becomes impossible to create regular squares with those entries. So n minus 1 is a minimum requirement. Some people are working in the opposite direction. Given an n by n array, what is the minimum number? What is the critical set or the minimum set that you need to make the regular square unique? So I'm doing a study both for Gregorian squares and lattice squares, and these are the critical size of the critical sets for Latin squares and Gregorian squares. There are some examples of the critical sets. These are all possible critical sets of order 3. Now I developed a game, needs a bit of trial and error. Okay, so we have ace of diamond, king of clubs, queen of clubs, ace of hearts. So this position becomes unique to jack of spades. This becomes unique. This becomes unique. And you have king of diamond, king of clubs. What are left? King of hearts and king of spades. King of hearts cannot be here. King of hearts cannot be here. King of hearts cannot be here. So only place for king of hearts is here. And king of hearts, king of clubs, king of diamond, king of spade has to be here. Now everything becomes unique. This is unique. And I could complete the Gregorian square in 0.77 minutes. So this is a nice game with one can play with cards. A demonstration. So I'll start from one. For one, does it go to zero? Okay, it goes to zero also. Let's start from one. So this is the Gregorian square of order one. For order two, it is impossible. Now, if you put 0, 0 here, 1, 1, you have to put 1, 1 here, but there is no possible entry here. 0, 1 is not possible because 0 is the first digit is matching and 1, 0 is not possible because second digit matching. So, second 2 is not possible. For 3, you can do a bit randomly. It's easy to create the Gregorian square of order 3. But if you throw in numbers randomly, it gets blocked. See, there is no choice for this entries. But if you, I have developed a modified random method that works. The 3 by 3 regular cube is complete. For 4 by 4, you just follow the natural way as I told. That completes 4 by 4. For 5 by 5, I'll put on the symmetry button. I'll put on the symmetry button and I pick up the numbers randomly. Oops. Oh, let me see. Now the lattice square is complete and I try my transversal finder and I'll be able to construct the orthogonal mate. So that completes the 5 by 5 usual orthogonal lattice square using transversal finder. And if you standardize, if you put it in the standard format, it's still symmetric and mutual orthogonal pair of order 5 exists. For 6, it doesn't, the mutual orthogonal pair doesn't exist. For 7, I'll start with an acyclic combination. So 0 goes to say 4, 4 goes to say 6, 6 goes to 2, 2 goes to 1, 1 goes to 3, 3 goes to 5, and 5 goes to 0. So if I start with this acyclic permutation, then 4 goes to 6, 6 goes to 2, 2 goes to 1, 1 goes to 3, and 3 goes to 5. So 3 goes to 5, 5 goes to 0, 0 goes to 4, 4 goes to 6, 6 goes to 2, 1 goes to 3, 3 goes to 5, 5 goes to 0, 0 goes to 4, 4 goes to 6. 5 goes to 0, 0 goes to 4, 4 goes to 6, 6 goes to 2, 2 goes to 1. 6 goes to 2, 2 goes to 1, 1 goes to 3, 3 goes to 5, 5 0 goes to 4, 4 goes to 6, 6 goes to 2, 2 goes to 1, 1 goes to. That gives me a Latin square of order 7. Now I can put it in the standard format. And then for the orthogonal, it's a Galois solution for order 7. No problem. So I take the first row as the diagonal because this is 2 times the number. So 4, 5, 2, 6, 3, 1. 4, 5, 2, 6, 3. Then I copy the rows 3, 1, 5, 6, 0, 2. 3, 1, 5, 0, 2. Then copy the row 2, 6, 1, 0, 3, 4. 0, 5, 4, 1, 6, 3. 5, 3, 0, 2, 4, 1. Six, 4, 2, 5, 1, 0. And the last row is unique now. Since the order is odd, I could use the acyclic permutation. So that completes the order 7 Greco square. For order 8, I'll use a trick. I'll follow the natural order for the Latin square. Galois field solution. It's Galois field 2 cube. So this is in standard format. And for its orthogonal mate, I'll just copy the rows with the proper column. So elements are 0, 1, x plus 1, x square plus 1, x square plus x square plus x plus 1. And the polynomial is x cube equal to x plus 1. So second entry in the first column is starting with x, then x square is 4, then x into x plus 1 is x square plus x, which is 6. Then x cube is x plus 1, which is 3. Then x square plus 1 into x cube plus x plus 1 plus x, which is 1. Then 7 should come here. That is the first column. Now I can copy the rows. 3, 0, 1, 6, 7, 4, 5. Copying the column means just adding with the top row. 5, 6, 7, 0, 1, 2, 3. Seven, 4, 5, 2, 3, 0, 1. 2, 1, 0, 7, 6, 5, 4. 0, 3, 2, 5, 4, 7, 6. It checks the Latin square property and the Greco-Latin square property too. It is taking time. 6, 5, 4, 3, 2. So that gives me a pair of mutually orthogonal Latin square of order 8. These two are Galois field solutions using Galois field 2 cube. Similarly, for order 9, I can use Galois field 3 square, but I won't do that. So that's the Latin square of order 8. For order 9, I shall use sequential method. Let me use sequential method. So start with 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8. Now 0, 8, then 1, 0. 1, 0, I'll start here. 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8. 2, 0, I'll start here. 2, 0, 1, 2, 2, 3, 6, 7, 3, 0. 3, 1, 3, 2, 3, 3, 3, 4, This is this gives me a Greco square of order 9, but this is not Galois field solution, and you won't get the complete set. 40, I'll start here. 40, 1, 2, 40, 4, 5, 6, 7, 8, and 50 will start here. 50, 51, 52, 3, 54, 55, 56, 57, 58, and 60, 1, 62, 3, 4, 65, 6, 7, 8, now 70, 71, 72, 73, 74, 75. It is doing all sorts of checks before putting the number and then putting the first choice. Then 80, 81, 82, 83, 5, 86, 87, finally 8. That completes the Greco square of order 9, and the method used is sequential method, which works fine for any odd order. For even order, it covers all the cells except the last n of them. Now for order 10, it's a different problem. I mean, there is the Galois solution. So the construction I know for order 10 Greco square or mutually orthogonal square is as forward, as follows. So you start with a 3 by 3 mutually orthogonal Latin square or 3 by 3 Greco Latin square. So on the in the corner top you put a 3 by 3. Then 3 4 4 5. I'll put 4 5. Then 5 6. Then 6 7. 7 8. Eight 9. Then 9 3. And that you do for first 3 columns and first 3 rows. So suppose you start with here. So you put 3 5 4 4 6 5 7 6 8 then 7 9 then 8 3 and 9 4. Suppose you start here 3 6 4 7 5 8 6 9 I'll put 6 9 then 7 3. After 9 it goes to 3. So 7 3 8 4 9 5. Suppose you start here 3 7 4 8. I'll do 4 8 and 5 9 6 3 7 4 8 5 9 6. Then for the third row you just start here 3 9 4 3 5 4 5 7 6 8 7 So that completes first three rows and first three columns. What left is the 7 by 7 grid. For that, for this row, we need to do a computer search. I don't know any better method here. I did it previously and got the order 10 regulating square or mutually orthogonal square, but it will take time, so I'm not running it. So this is the way one can construct the order 10 regulating square. There should be other methods and other type of regulating squares of order 10, not having a 3 by 3 on the top left. This is a well-known method. And I demonstrate one more thing. So I have an algorithm to create a random Latin square. It is just putting the numbers randomly. And then I have an algorithm to turn it to a Latin square by doing corrections. And that converges. 59. Okay. Now let me adjust it. From 67 it went to 93, only 7 cells left, 94, 96, only 4 cells left, 98. Finally the algorithm converges, giving me a Latin square of order 10. Now I'm doing the same for the second Latin square in the hope of getting a pair of mutually orthogonal Latin square, but that algorithm is not converging. It is not converging when I apply it on a pair. Maybe someday we'll get. It is taking time. I'll pause the video probably. Talking for more than an hour now. 39. 1. Okay, 67. So we have 100 entries in the left Latin square, 67 entries on the right Latin square. But when I'm trying to adjust the entries in the right Latin square to make it 100, okay, so when I am reaching 10% on the right Latin square, it is becoming 61% in the left Latin square. So this method is not working for a pair of modes. It is not converging iteratively. Anyway, this is the order 10 Greco Latin square or mutually orthogonal Latin square I got on 5th of March. Uh, this is a pair I got on 3rd of July. at 8:19 p.m. and 8:27 p.m. at a difference of 8 minutes. Here, the first three rows and first three columns are same for both the mutually orthogonal Latin square. Only the 7 by 7 part is different. So I call them twin modes. Here is a triplet, but not of order 10, but of order 9. Here the first three rows and first three columns are same. Only the 7 by 7 portion, 6 by 6 portion inside is different. I got it on 8th of June. Okay, finally some references. I have this book, Orthogonal Latin Square Pastel Groups by Anthony Evans, Latin Squares and Their Applications by Kidwell and Deans, and the Permutation Group book by Dixon. Here are some interesting papers. This paper talks about this paper. We know that Castaneri proved that that Greco-Latin square of order 6 doesn't exist by exhaustive computation, but later we have got some logical proofs, and here is one of them by Stinson from Canada. A short proof of non-existence of a pair of orthogonal lattice squares of order 6. Here is a logical proof. And this is the Bose and Seconded paper, where they first produced the counterexample to Euler's conjecture constructing a 22 by 22 Greco-Latin square. This is by Bose and Seconded, and this is the 1959 path-breaking paper by Bose, Seconded, and Parker, showing that mutually orthogonal further results on the construction of mutually orthogonal Latin square and the falsity of Euler's conjecture. After this paper, they are called Euler spoilers. Here is a game available in Play Store and App Store on Latin squares and Greco Latin squares. And here is our table where we first had a look at the Latin squares and the Greco Latin squares of different orders. Here are Latin squares, and then there are Greco Latin squares. This is the 10 by 10 mutually orthogonal Latin square, where it starts with the 3 by 3 mutually orthogonal Latin square on top left corner. Thank you. I'll stop here.